FPGAs are just incredible pieces of technology, right? They're like digital clay. You can mold them into pretty much any circuit you can dream up. But have you ever stopped to think about how all those little pieces inside actually talk to each other? How do they all connect to bring your design to life? Well, that's what we're diving into today. The secret sauce, the thing that makes it all possible, is something you almost never actually see: the routing network. Honestly, the best way to think about it is as the chip's central nervous system, or maybe a massive hidden highway system. It's the absolute critical infrastructure that wires everything together, letting signals zip around and making the whole thing work. So, what exactly is this routing network? Well, at its core, it's this huge web of pre-laid wire segments and programmable switches. That's it. Its only job is to create custom pathways between all the logic units and the I/O blocks. It's literally building a personalized highway system just for your circuit's data. Okay, but this is where we hit the fundamental problem at the heart of every single FPGA design. It is a constant tug of war between two big ideas: flexibility and efficiency. How do you build a chip that can become anything while also being fast, small, and not burning a ton of power? See, an FPGA's superpower is its incredible flexibility. But, and this is so important to get, that exact same superpower is also its kryptonite. All of that programmable wiring and switching adds overhead, and that means FPGAs are almost always going to be bigger, slower, and more power-hungry than their custom-built cousins, ASICs, which are designed to do just one thing, but do it perfectly.
To really get a sense of the price you pay for that flexibility, just look at this number: 90%. That's not a typo. Up to 90% of the entire area of an FPGA chip can be taken up by just the programmable routing. And that's not just a space issue. All those wires have capacitance, so every time a signal travels, it costs energy. So you're burning a huge amount of power on just communication, not even the actual computing. It's a staggering trade-off.
And this analogy just nails the difference. Think of an FPGA as a dense city grid, like Manhattan. You have amazing flexibility, right? You can take a million different routes to get from one point to another. But it's not always the fastest way, and it takes up a ton of space. An ASIC, on the other hand, is a bullet train. It has one single, fixed route, and that's it. But man, it gets you from A to B with unbelievable speed and efficiency. Okay, so we know the challenge is huge. How in the world do chip architects actually design these routing networks? Well, the most common solution, the one you'll find in basically every FPGA out there, is called the symmetrical or island-style array. And it's called island-style for a reason. The logic blocks are literally like little islands, and they're floating in this vast sea of routing wires. The sea is all organized into a nice, neat grid of horizontal and vertical channels. Now, the number of wires in each channel is called the channel width, and deciding on that width is this incredibly high-stakes balancing act. If you make it too narrow, you can't route complex designs. If you make it too wide, you're wasting millions on silicon area that nobody's even using. Let's break this picture down. The configurable logic blocks, or CLBs, those are your islands. That's where all the real work, the computation, happens. To get signals on and off those islands, you have connection boxes, which basically connect the island to the sea of wires. Then, to make a turn at an intersection, signals go through a switch box. This lets a signal traveling horizontally switch over to a vertical track. It's this simple, regular grid that makes the whole architecture so powerful and versatile. But the island-style grid, as popular as it is, isn't the only way to build an on-chip highway system. Let's check out two other architectures that have a completely different philosophy about how to solve this problem: row-based and hierarchical designs. So first up is the row-based architecture. Instead of that uniform sea of routing, I want you to picture a layer cake. You have a row of logic blocks, then a big, thick channel of routing wires, then another row of logic, and so on. This design is all about those horizontal connections, giving you these super wide, fast data paths. It's perfect for things that have a really predictable data flow, like a signal processing pipeline where data just moves linearly from one stage to the next. And this diagram shows it perfectly, right? You can see those really distinct bands, rows of logic separated by these wide parallel channels for the interconnect. It's a much more structured layout than the city grid of the island style, and it's totally optimized for designs where data flows nice and cleanly, row by row. Okay, the third approach, the hierarchical architecture, is really clever. It's built on this simple observation.
In most circuits, the things that need to talk to each other a lot are usually placed close together. We call this locality of connection. This architecture takes advantage of that by grouping logic blocks into clusters, and then connecting those clusters in a hierarchy, kind of like a corporate org chart. So for example, a processor's math unit and its local cache would be in the same cluster, giving them blazing fast communication and saving a ton of power.
Looking at this diagram, you can see how it works. You have these small clusters of logic blocks. Connections inside a cluster are super short and super fast. If a signal has to go to a different cluster, it travels up the hierarchy to a bigger interconnect and then back down. It's an incredibly efficient system for local communication, basically keeping all the busiest traffic on the local roads instead of clogging up the main highways. All right, so we have our three main contenders: the general-purpose city grid, the structured layer cake, and the efficient org chart. So how do they really stack up against each other? This table really lays out the physical blueprints nice and clean. Symmetrical is your classic grid of islands in a sea of routing. Row-based is your layer cake with alternating rows and big horizontal channels. And hierarchical is all about grouping logic into clusters that are connected by a tiered system. Three very different ways of building the chip. But what does all that mean for performance? Well, the symmetrical array is super flexible, and its regularity makes it much easier for the software to automatically place and route circuits. That's a huge reason why it's still the most common choice. The downside is that it can be inefficient for really local connections. The row-based style, as we said, is great for linear data flows, but it really struggles with more complex, messy routes. And the hierarchical style is an absolute champion for speed and power, as long as your design has strong locality. If distant clusters need to talk a lot, you can create some serious bottlenecks. And that kind of brings us to our final question. The island-style architecture is the undisputed standard today for a lot of good reasons. But as our circuits get way more complex and our thirst for performance and power efficiency just skyrockets, is it going to be enough? What do you think the next generation of these on-chip highways is going to look like?